Are you prepared to relinquish everything you assumed you had some awareness of the idea of time? To put it briefly, there is no such thing as time, and it's not simply us saying that, rather, it's the consequences of new research. But what is implied by this radical assumption? Why could what we usually comprehend as time actually be just a deception of quantum physics? And what conclusions can be drawn from this revolutionary presumption? Albert Einstein once said, "For us physicists, the distinction between past, present, and future is only an illusion, albeit a stubborn one." Abstract time, with its emphasis on the now, has no objective meaning, and indeed, the more we study this concept, the clearer it becomes that what seems so straightforward in our daily lives could not be stranger. While time often represents merely numbers on a clock or a particular date on the calendar, we usually overlook the question of what time actually is. By definition, we are dealing with a physical quantity that describes the sequence of events in a unique, irreversible order, and it literally affects everything. The universe, in addition to moving spatially, also advances through time, from its beginning in the Big Bang to its end. Time is completely linear, and yet it continues to present new puzzles to this day. As mentioned at the beginning, a new study has now concluded that time isn't a fundamental component of the universe at all but merely an illusion that results solely from quantum entanglement. But what does that mean? Does this imply there is no beginning or end to our present reality? Unfortunately, it's not that simple to understand why time has become the focus of countless scientific discussions. To approach this, we should first consider the various perspectives available to scientists. On the one hand, there is Einsteinian physics, which explains the processes of the universe on a large scale. On the other hand, there is quantum mechanics, which deals with phenomena on a very small scale and often appears to contradict classical physics. Let's consider Schrödinger's cat, a thought experiment published by the physicist Erwin Schrödinger in 1935. In this scenario, a cat is locked in a box with a deadly poison, but no one knows when the poison will be released. Consequently, the cat can be considered both dead and alive at the same time. Its state would only change to one of the two outcomes through direct observation. But what does a cat in a box have to do with quantum mechanics? It's very simple. Quantum mechanics also recognizes a superposition like this, a superimposition of different states. Only when a measurement or observation is made does the corresponding system assume one of the superimposed states. Schrödinger's focus at the time was to illustrate the incompatibility of quantum mechanical and classical physical principles, because a cat cannot be both dead and alive at the same time. The wondrous world of quantum entanglement, however, goes beyond superposition. Quantum physics not only recognizes superposition but also quantum entanglement. According to quantum theory, particles do not have definite states, they can be assigned relative probabilities for being in one state or another, and this only collapses to a single state upon measurement. It becomes even stranger when two particles interact with each other because they can become entangled. In other words, their individual probabilities are no longer independent but coupled to each other, forming part of a complex probability function describing both particles. To better understand this, let's look at the following example. In an experiment on entanglement, two electrons are produced simultaneously, and their spin, or intrinsic angular momentum, is measured in two separate devices. Ultimately, it turns out that the electrons each have opposite spins, which is surprising given that, according to superposition, their states were undetermined before measurement. The fact is, it was only the measurement that caused one particle to take on one state and the other particle to take on the opposite state, despite their spatial separation. The two electrons are thus recognized as a coherent system. Quantum entanglement also defies the locality assumption, which states that processes only immediately affect their direct spatial surroundings. In the case of quantum entanglement, the entangled particles can be light years apart and still be inseparably linked, instantly exchanging information. Unsurprisingly, Albert Einstein had issues with this so-called spooky action at a distance, as it would require information transfer at speeds faster than light. Although the principle of quantum entanglement sometimes seems very confusing, it might now offer researchers the opportunity to finally uncover the true nature of time. Is time simply an illusion? According to a study published in Physical Review, the lead authors from Italy's National Research Council argue that it is possible to reconcile time with both classical physics and quantum mechanics if it is viewed as an appearance arising from entanglement. In quantum mechanics, time embodies a fixed phenomenon, a relentless flow from the past to the present. However, time remains external to the peculiar, ever-changing quantum systems and can only be understood by observing changes in external units, such as the hands of a clock. According to Einstein's general theory of relativity, time is intertwined with space and can even be warped and stretched. Due to this discrepancy between classical and quantum mechanical laws, scientists were at an impasse for some time. However, the aforementioned study now suggests that time may just be an illusion resulting from quantum entanglement. But what does that mean? The time problem isn't new in quantum mechanics. As early as 1983, the Page-Wouters mechanism proposed a theory that states time for an object only emerges through quantum entanglement with another object that acts as a clock. For an unentangled system, there is no time at all, and the system views the universe as frozen and timeless. By applying this mechanism to two theoretical quantum states, a vibrating oscillator and a group of small magnets acting as a clock, the researchers observed that their system could be described by the Schrödinger equation, which predicts the behavior of quantum objects. This occurred without the explicit use of time. The role of the clock was taken over by the conditions of the small magnets. In the next step, the researchers repeated their measurements twice more, first, assuming that the magnetic clock and then the oscillator embodied observable, or, in other words, larger objects. Their conditions improved to those of classical physics, showing that the flow of time is a result of entanglement, even for objects on a large scale. In this context, the researchers emphasized that the correct, and above all, logical approach for them is to start from quantum physics and understand how to derive classical physics from it, not the other way around. Other researchers, however, have been somewhat cautious in their statements. Although it is mathematically consistent to envision universal time as entanglement between quantum fields and quantum states of 3D space, no one knows whether this view will lead to something new or productive, such as changes to quantum physics and the general theory of relativity. What does Michio Kaku say about time? Suppose we've truly been misunderstanding time all along. Wouldn't it also be possible that one day we could uncover properties that currently seem completely unimaginable? Well, that's precisely what Kaku was asked during an interview. More specifically, the world-famous physicist was asked to share his thoughts on the nature of time and time travel, and he had truly astonishing things to say. But listen for yourself. Here's a quote. Let's start with Isaac Newton. Newton believed that time is like an arrow. Once shot, the arrow moves in a straight line. 1 second on Earth is the same as 1 second on Mars, 1 second on Jupiter, and so on. The arrow never changes course. But then along came Einstein, who said, not so fast. Time is like a river, a stream that bends, speeds up, and slows down. The question that concerns us so much is this: can the flow of time possibly split? Can it form multiple stream arms, or is it possible for it to form loops and circle around itself? In that case, time travel is something we need to take very seriously, since Einstein's equations allow for passage through time. And the concepts for time travel are actually compatible with Einstein's theories. For example, with massive rotating cylinders, you could move around the cylinder and return before you left. Reality is like a kind of rubber, like a trampoline net. If we stretch the trampoline net enough, it can tear, and maybe we can shape the trampoline into a pretzel, which would allow us to travel back in time. But unfortunately, as always, there is a catch. The energy required to do this is immense. Not even a nuclear bomb has enough energy to power a time machine. For a time machine, we would need the energy of an exploding star. As is well known, the theoretical question of time travel is accompanied by certain paradoxes. For example, what would happen if we killed our grandfather before he had children, thereby preventing our own existence? According to Kaku, there are two ways to resolve these troubling thought experiments. The first way is called self-consistency. Even if we aimed a loaded gun at our grandfather, something would prevent us from pulling the trigger. It simply wouldn't be possible, and further, perhaps there is some hidden physical law that stops us from creating time paradoxes. But I don't think so. I believe that the flow of time splits in such cases, just as we see it in Back to the Future. That's the simplest way to explain time paradoxes because we don't have to add any further assumptions except those of quantum mechanics. If we travel back in time and save Abraham Lincoln from the assassination attempt, then we would have saved a different Abraham Lincoln. If you shoot your own parents before you're born, then you've actually shot someone else's parents. If you will, we create a parallel past. Even Stephen Hawking said that there must be some physical law preventing us from turning back the clock, and we've looked for it but found nothing. We know of no laws of physics that prevent us from traveling backward through time. It appears to be compatible with the laws we know. The thing is, we'd need the energy of a star to do it. The civilization that accomplishes this would have to be highly advanced. But it's not impossible. Thank you for watching this video. I hope you enjoyed this journey into the mysteries of the universe. If you found this video interesting, please give it a thumbs up and share it with your friends. Don't forget to subscribe to my channel for more amazing updates.